Okay, I guess we can begin. So thank you all for coming to this week's Colloquium talk. The main, I guess, motivation behind this talk was that we, I guess, wanted to give something that was slightly more accessible to like first years or like lower year students in general, because the previous talks were like on algebraic geometry and some of you complained. So today the material should be fairly light. Anyone should be able to understand this. I mean, at some point, some of the examples we'll see might involve some more like, I guess, advanced notions, but globally it's quite accessible. So what is a continued fraction? I'm going to go over what are continued fractions, interesting applications, and then a specific constant related to continued fractions, called Kinchin's constant, and then finally we'll go over something called So what are continued fractions? Continued fractions are fractions with a denominator that is a sum that contains another continued fraction, right? So this is, I guess, your fairly prototypical example. And notice how the numerators are all ones. And this is called a simple continued fraction. And the denominators, so this can be equal to 0, or I guess can be a negative number. But these numbers here in the denominator are positive integers. A few examples. The first one's fairly standard. For pi, we have this very interesting continued fraction. And I guess it's really easy to think of how to calculate them. Other continued fractions, if you're interested, e. So if you see there's a pattern here, it goes 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1. Gamma here is the Euler-Mascheroni constant, and there's no pattern that has been found so far. And you can find a continued fraction representation for every single real number. Let's go over a word example. Let's consider this number 58 over 13, which, as you can see, is approximately 4.4615. Now, the way you do this is kind of fairly straightforward. I'm sure that even if I didn't give this talk, you guys would probably be able to figure it out on your own. Well, I guess first you isolate the integer part. So we know that this is equal to 4 plus some fraction. And we look at this fractional part, right? 0.4615, which is equal to 6 over 13. Now, since our continued fractions have 1 in the numerator, that means you want to look at the reciprocal. So we first take the reciprocal, which is 13 over 6, approximately 2.166. We can again isolate the integer part, and then again take the reciprocal of that. So we know that another closer approximation is 4 plus 1/2, right? We see we're getting closer, but we're not done yet. Once again, we have to isolate the fractional part and take the reciprocal. So since 13 over 6 is equal to 2 plus 1/6, I guess in this case, this is really such a simple example because the final fractional part, 1/6, has 1 in the numerator. So this is its own continued fraction representation. And so we end up with 4 plus 1 over 2 plus, if I'm not mistaken, if I was, that would be quite embarrassing. There we are, 4 plus 1 over 2 plus 1 over 6. Let's go over another example, which I guess is a bit more interesting, because working with, I guess, rational numbers is kind of boring. What's the continued fraction representation? By the way, I'm really sorry that the chalk is really thin for some reason. This chalk is not good. What's the continued fraction representation of square root of 2? Well, we know that, what is square root of 2 approximately equal to? Like 1. Yeah, it's like 1 plus some fractional part, x, right? We can square both sides, which gives us 2 plus 1 plus 2x squared, right? We move this one to the other side. This gives us 1 is equal to 2x plus x squared. This is super easy so far, right? It's just high school material. Divide both sides by x. You get 1 over x is equal to 2 plus x. And then take the reciprocal, and you end up with this identity. X is equal to 1 over 2 plus x. And that gives us, said something? Oh, yeah. And this gives us a sort of recursive formula for how to calculate the continued fraction, right? Because we know that square root of 2 is 1 plus x. but that's equal to 1 plus 1 over 2 plus x, which is equal to 1 plus 1 over 2 plus 1 over 2 plus x. And I guess you can see where this is going, right? So the continued fraction representation of square root of 2 is 1 plus, and then a whole bunch of 2's infinitely down. So what are the advantages of the continued fraction representation? Actually, there are many advantages. And, well, first of all, some of you might have guessed already that the continued fraction representation of a real number is finite if and only if it is rational, right? Because every rational number is a fraction, and so you can write it as finitely many continued fractions. And the continued decimal, whereas the decimal representation of a rational number may be infinite, you know? If you look at 1/3, well, the continued fraction representation is just 1/3, whereas the decimal representation is infinite. And the simple continued fraction representation of an irrational number is unique, whereas for the decimal representation is not necessarily unique. It's also really easy to calculate reciprocals, right? If you have some continued fraction, well then simply shifting it by 1, shifting your sequence of denominators to the right and then adding 0 gives you the reciprocal, which means that if you have, okay, this is way better. A0 plus A1, and so on. This number is the reciprocal of 0 plus 1 over A0 plus 1 over A1, which I guess is a neat trick. But the most important application, or I guess the most useful application, would be that successive approximations that are generated by truncating your continued fraction representation give you, in a certain sense, the best possible approximation to your irrational number, right? Meaning that if you have some sort of continued fraction, A0, and so on, then truncating it every time, this gives you the best possible approximation to your irrational number. So what exactly do we mean by best possible approximation? Well then, basically these initial segments that are taken by truncating your continued fraction are called the convergence of the continued fraction. And so by best possible, we mean that, okay, let's say you have your irrational number. Was a rational number n over d is the best possible rational approximation if n over d is closer to your irrational number than any other n over q, where q is less than or equal to d. That's what we mean by best possible in this case. And so actually, when you have an infinite continued fraction, the convergence will generate every single time the best possible rational approximation to your irrational number. The actual algorithm for proving this is like kind of technical and it's long, and I'm not going to go over it, but you can find it on Wikipedia, and it's not too hard to understand. And so obviously, I guess it follows that the larger your convergent is, the closer you are to your irrational number, right? If you have some sort of continued fraction that's like, I don't know, 1 plus 1 over 2 plus 1 over 500, well then you know that if you truncate at this point, you're going to be very, very close to the desired value, right? Because the other terms that come after are kind of irrelevant. If you guys remember earlier, when you looked at the continued fraction representation for pi, which was, where was it? Here. You see that there's like a 292 here in the denominator, which means that if we truncate our continued fraction at this convergent here, we are very, very close to the value of pi that we want, and we don't really need to look at more terms in our continued fraction. And that's why pi actually as a number can be very well approximated by rational numbers. Well, I guess the natural question to be, what is the number that can be least well approximated? What do you guys think it is, based on what we said so far?
10.
Well, 10 is an integer, so its approximation is itself. Now, what continued fraction, since we've said that larger terms in the denominator mean good approximations, what would the least well approximated irrational number be?
1 over 1 plus.
Exactly, it's just an infinite sequence of ones, right? And so I guess a question to be, what is this number equal to? some of you may already know this. It's like very, I guess, it's a very pop science-y result. You've probably seen like YouTube videos about it, but I guess it is fairly, and it's super easy to derive, right? Well, can anyone think, the same way we did for square root of 2, right? For square root of 2, we found this sort of recursive formula. Can anyone find me a recursive formula for this continued fraction? Yes?
I mean, it's like x is equal to 1 plus 1 over x.
Exactly. You have x is equal to 1 plus 1 over x, right? Because you can just keep on replacing x every time, you get this descending, infinite descending chain of ones. This is actually the hard part, because from now, well, we can just square both sides, right? And we have a polynomial. Does anyone know what the roots are to this polynomial? No? Well, it's a number called the golden ratio, right? Which is equal to 1 plus square root of 5 over 2. You guys do know what the golden ratio is, right? We've seen these videos about, like, you know, the snail and the...
What about the other root?
Yeah.
Well, we're only looking at positive integers, right? Because it's 1 plus.
Oh, okay.
Yeah. And so the golden ratio has some interesting properties. And most notably, there's this famous theorem by Hurwitz, a number theory, which says that for all irrational C, there's just infinitely many co-prime integers such that this holds. And if you'll notice, there's a square root of 5 here, right? And actually, this square root of 5 is the optimal constant. Because if we chose any number that was slightly bigger than square root of 5, that would make this fraction smaller, so it would make your bound tighter. Well, the theorem would fail for the golden ratio. So actually, in a sense, the golden ratio is like the most irrational number, because it is the least well approximated by rational numbers. Another interesting property about the convergence related to this infinite fraction of ones that we've seen is that the convergence of phi are ratios of successive Fibonacci numbers. And finally, one last, I guess, fun fact about the golden ratio, and this is, I guess, this is actually really easy to derive, but it just looks really cool, is that we have this, which is, I guess, it's weird, but it's, right, it's kind of sick, I think. Actually, so we've seen how to derive this identity here, but this one here is also very easy to derive. And I guess I'll leave it to you as an exercise. It really shouldn't take more than like 5 minutes. Now we'll explore some interesting applications of continued fractions and like areas of math where continued fractions arise where you wouldn't really expect them to. And this is maybe the first example I'm going to give is something that is not necessarily something you might have seen before if you were in first year. How to construct a non-Borel set. So first of all, what is a Borel set? A Borel set is, I mean, if those of you who have taken maybe like measure theory know what it is. But I guess it's any set that can be formed from open sets under the operations of countable union and countable intersection and relative complement. That's what a Borel set. If you take countable unions, countable intersections, and relative complements of open sets, well then the result is what you call a Borel set. Does anyone, I guess, have an idea of what, I mean, does countable union, countable intersection, relative complement remind any of you of something?
Ooh, ultrafilter.
No.
No.
So it's not that deep. Sigma algebras, all right? If you guys don't know, a sigma algebra is a collection of sets that is closed under countable union, countable intersection, and relative complements. And so the collection of all Borel sets on your measure space is called the sigma algebra, or the Borel algebra of your sets, right? And so the point is that you, using continued fractions, you can construct a set and give an explicit construction of a set that is non-Borel. And so this is the construction. So, as stated earlier, every irrational number has a unique representation, right? You can write it by this simple continued fraction, where this one, I guess, can be positive or negative, and these are all positive integers right here. Now, let A be the set of irrationals with the following property. There exists an infinite subsequence of your simple continued fraction, such that each term divides the next one, right? So I guess we could sort of give an example of like an irrational number. let's say there's some subsequence. Chris, can you order the pizza? I mean, thing is, it's kind of, it would be hard to construct actually an explicit counterexample, because you would want your first one to sort of divide infinitely many. So it would be like, I don't know if you can explicitly draw an explicit example of one. But the main idea is that this set is definable. And the conclusion, I guess, is that this set A is non-Borel. Now, I'm not actually going to prove this, because it's very technical and we don't have time. If you guys are interested in more descriptive set theory, there's also another use of continued fractions, and you can basically construct a homeomorphism between the bare space, which is n to the n, right? Which is just like infinite sequences of natural numbers, and you can prove that this is homeomorphic to the set of irrationals. And once again, I will not prove this, but you can find it online. And I guess, I mean, I sort of, even though I will not prove this, I guess I sort of owe it to you to explain why this is true. Well, actually, it depends on how many of you have taken like set theory before. How many of you have taken set theory? Just, you haven't taken. Okay, who wants to sort of hear like the explanation for why this is true? We can skip it over. All right, okay, fine. So the general idea is that there is, so if you have a binary relation on a set, you can have a set that a relation is basically called well-founded if there is a sort of minimal element with regards to your relation, right? And so it means that there is no infinite chain, infinite descending chain, such that if you have like R is your is a binary relation, well then you sort of have, there does not exist an infinite descending chain of like elements. This is called a well-founded relation, right? And so you can look, if you have a set S, the set here is just basically the set of all well-founded relations on your set S. So the thing is, this set is non-Borel either, and I don't actually know the proof of this. But the main idea is that because this set basically relies on a property of there not existing some infinite chain that satisfies a property. And this example here is based on having an infinite chain that satisfies some sort of property. What you can do is sort of find a Borel isomorphism between your set A here and the complement of the set SWF. And this will prove that this set is non-Borel. Let's move on. Another interesting application of continued fractions is the Minkowski question mark function. If those of you who have taken maybe real analysis before have seen this question show up as like a very useful counterexample, and we'll see why. So this is the definition of your Minkowski question mark function. It looks really strange, right? But the motivation behind it is that, okay, let's start with like some random string, right, of bits. So a string of zeros and ones. Let's say we have, I don't know, 11.001, 001, whatever, right? This is a real number, but we can obviously interpret this as a binary number, right? And actually, as a binary number, this is equal to pi. So take the fractional part, right? So which is 0. Whatever. And basically, the trick here is that you replace each consecutive block of zeros or ones by the length of the block, right? So we know that this number is equal to pi. So pi is equal to 3 plus the fractional part. So we replace each length of zeros and ones. So we have, so the first section, the first, I guess, fractional part would be length 3. And then you have 1, 1. And then you have 2 zeros, another 1 here, and then 4 zeros, and so on. And this gives you a sequence of numbers, right? 3 is your integer part, and then you have 3, 1, 2, 1, 4, 6. You can look at the continued fraction made by this number, right? So we get a continued fraction. 1 over 3 plus 1 over 2, and so on. And what number does this give us? This gives us a number that is like approximately equal to 3.2676. And so what the Minkowski question mark function does is yes. So what the Minkowski question mark function does is that it basically reverses this process. So in our case, we have that question mark of 3.2767676 is equal to pi, right? It is like the motivation behind it is still kind of weird. Like I don't know how you would come up with this, but that's kind of the idea behind this function. Is that it sort of reverses this like run length encoding of your continued fraction. Now, why do we care about this function, or at least why is it interesting? Is that because, as I said, it has a lot of useful properties that make it a counterexample. It is strictly increasing, but it has zero derivative almost everywhere, which seems strange, right? Because normally you would expect that a function that has zero derivative almost everywhere is constant, and yet this function is strictly increasing. Not only that, it maps rationals to dyadic rationals, and quadratic irrationals to other rationals. So, what is a dyadic rational? Any of you know? Nick, don't you know this?
I forgot.
A dyadic rational is just a fancy way of saying that like that it's like the bits or like the expansion of your number is like in base 2, right? Or it's like it's only powers of.
Oh, so it's like localization at 2.
Yeah, you can, if you want to look at it from an algebraic perspective, you can say localization at 2. But the point is that since basically rationals get mapped to rationals, and then you have these quadratic irrational numbers, so roots of quadratic polynomials get also mapped to rationals, it follows that if pi of x is irrational, then either x is algebraic, but is degree greater than 3, or greater or equal to 3, so greater than 2, or it's transcendental. And there are actually many other interesting properties of the Minkowski question mark function, is that, well, the graph of question mark of x is a type of fractal curve known as a de Rham curve. A de Rham curve is basically any continuous image of a Cantor space, and a Cantor space is any topological space that's homeomorphic to the Cantor set. You guys know what the Cantor set is? Yeah, it's like this sort of, infinite like line thing where you just keep on moving thirds. And so if you take any topological space that's homeomorphic to the set, then there's a continuous function which maps it onto the graph of question mark over x. And this is what the graph looks like. So actually this has zero derivative almost everywhere, even though we see it increasing. That's because the jumps which happen here are like, have derivative, infinity, I guess. It's like flat and then it just sort of jumps up. But it is continuous. Yes?
Does the derivative exist almost everywhere? Or does
Yeah,
it?
so the derivative exists almost everywhere. And where it exists, it's equal to 0. Right? But this function is continuous. I guess, how much time do I have?
The function is also similar to like devil's staircase.
Yeah, well, I mean, the devil's staircase is another example of like, I guess these functions are all called singular functions, if I'm not mistaken. There's functions that have zero derivative almost everywhere, but that they are strictly increasing. And so another example is, as you mentioned, the devil's staircase. And there's a lot more, I think. There's like a Vitali sort of function or something. Now we're going to go over a specific constant which is linked to continued fractions. It's called Khinchin's constant. So there's this theorem which says that if you have any real number x, which was written this way in its continued fraction representation, it is almost always true that taking the limit of the geometric mean, so obviously if you have a set of numbers, the arithmetic mean is just taking the sum and then dividing by how many items you have, right? The geometric mean is taking the product and then taking the nth root. So this theorem says that taking the limit as n goes to infinity of the geometric mean of the denominators, notice how we're ignoring the first part, right? Just the denominators of your continued fraction representation. Well, it is almost always true that this limit converges to this weird number right here, which is called K0. And K0 is approximately equal to 2.685. This is the sequence in the OAIS, if you guys are interested. So, can someone tell me why almost always true, based on some things I've said previously during this talk? Yes?
Take one.
Yeah, the number 1. I mean, yeah, like, I guess more generally, for any rational number, this is not true, right? Because we know that rational numbers have finite continued fraction expansions, and so obviously this is false for rational numbers. Yes? Yes, for the golden ratio, it's not true as well. And actually, it's not true for any quadratic irrational number. So for any root of a quadratic polynomial, this theorem doesn't hold. So that's why it's almost always true. Actually, it doesn't even hold for some transcendental numbers. We know that this is false for E, right? So it doesn't work for E. Yeah, so why almost always true? We didn't know this. So I'm going to go over a quick sketch of the proof of this theorem. This theorem actually, the proof is very interesting because it uses something called ergodic theory. So I mean, I guess if you really want to know the idea behind it, you would need to know like some measure theory, but it is fairly accessible. And I'm not going to go over every single detail in the proof, that's why it's a proof sketch. So as I said, in the theorem, we're ignoring the first coefficient, right? Like we're looking at the geometric mean of A1 to AN. We don't start with A0. So since we ignore the first term, and since the irrationals anyways have measure 0, right, it just suffices to study or to limit ourselves to the irrational numbers in the unit interval. So we first define a map, which is just shifting your continued fraction by 1, right? If you look at the denominators, A1, A2, you just sort of ignore the first one, and you map it to this number. The specific name for this, I think, is called the Gauss-Kuzmin-Wersing operator. Now, for every Borel subset E of I, so I think you guys now know what Borel subsets are, is that right? So for every Borel subset, we can define this following measure. Don't ask for the motivation behind this, but this is the proof. And you define this measure, right? And so the advantage of this is that, well, okay, first of all, mu is a probability measure on the sigma algebra of Borel subset of I, and it's equivalent to the Lebesgue measure on I. And the advantage of this measure, because if it's equivalent to the Lebesgue measure, why don't we just take the Lebesgue measure instead of just taking this weird new measure, is that this measure is preserved by your Gauss-Kuzmin-Wersing operator. And that's a very desirable property. And I guess the hard part of the proof, which I will skip over, is that T, this map T, is what is called an ergodic transformation on your measure space. So you can Google what ergodic transformation means. I'm not going to explain, I'm not going to prove what, but you just have to sort of believe me on this. Now, because T is an ergodic transformation on this measure space, we can apply something called the ergodic theorem. So what the ergodic theorem says is that if you have any function f that's mu integrable on I, well then the average value of f of applying your shifting map, tk, is the same for almost all x. This is kind of what it means, is that the average is equal to this. We have this integral identity. And so in our case, what we want to do is that we just want to replace the function f by taking the natural log of the first term here. And so replacing f, we get this identity right here. And so can anyone tell me what the final step of the proof is? Actually, I guess it's not fair because you guys don't really remember the identity. But the main idea is that we just exponentiate on both sides, right? So this becomes the geometric mean, and this, and then here cancels, right? Take an exponential on both sides, and we are done. And the theorem has been proven. So what are some open problems related to Khinchin's constant? So although almost all real numbers satisfy this property, it has not been proven for any real number that has not been specifically constructed for the purpose. Which I guess is kind of strange, right? Because it means we really don't know that it works for any number. And that all the examples where we know it works, we sort of made up convoluted examples where it works. So notably, I mean, I said it doesn't work for E, But, you know, what about for pi, right? What about for, I don't know, pick your favorite transcendental number, and we don't know if this is true for them, right? What about pi? What about Apres constants, zeta of 3, which we know is irrational because of the talk yesterday that was given here. Actually, we don't know if this is true for Khinchin's constant itself. Not only that, is Khinchin's constant algebraic or transcendental? We don't know. Is it even irrational? We don't know. So if any of you are interested in, I guess, you know, measure theory or like analytic number theory, these can be very interesting questions to tackle later on. There is, I suppose, one more topic that I'm going to talk about today, which are Trot constants. And this is, it's just like a weird sort of thing that exists. So a Trot constant is a real number whose decimal digits are equal to the terms of its continued fraction, right? So here's an example, right here. We have 0.1084, whatever is equal to its own continued fraction. So why is this kind of cheating? There's something about this that I don't like, because it's kind of, I guess it's kind of cheating in a way. Well, we have zeros here, right? Yeah, so it's kind of bullshit. I don't know. Yeah, the main idea is that this number is somehow equal to this. So the thing is, the way this was shown is actually not, there's no theorem that proves existence or uniqueness of this. The way Mr. Trot found this constant was actually just by an algorithm on like Mathematica. So yeah, a bit of cheating involved. And yeah, very little is known about the existence and uniqueness of some numbers, and so this was found algorithmically using Mathematica. There are a few other numbers that have been found, but I think it's even more cheating because they're not even simple continued fractions. They're generalized continued fractions, and so the numerators are also different to 1. And I think that's a lot of cheating. But the point is, we really know nothing about these numbers. There's actually only one thing that we know, is that regarding the set of Trot constants in base B, and this is also going to be like a really weird fact, but they discovered it. If your number B is equal to 3, or is between a square and the square plus like the square root, well then the set of Trot constants in base B is uncountable. So I guess notably in all the bases we care about, it is uncountable. So it's true in base 3, it's true in base 2 as well, since base 2 is between 1 and 2. It's true in base 10. It's true in base 12, right, which is superior to base 10. And in all other bases, the set of Trot constants is empty. And that's about the only thing we know. But it is, I guess, you know, sort of, it is a natural question to ask and a natural direction to explore. But there is really not much research that has been done on this. And that's it for today. Any questions? Yes?
So for multiplicative inverse of the sequence, you just have to shift, right?
Yeah, you just have to shift it.
Inverse?
Wouldn't you just have to change the sign in your? No, that's not true.
So it should
I don't
be
think so.
positive.
I don't know actually. That's an interesting question. I don't think shifting the sign works, does it?
I mean, you can't change the sign, right?
Yeah, you're
It
not
should
allowed
be
to change the
positive.
sign. Well, I mean, one thing, but it's also a bit of cheating, is that if you have a0 plus 1, whatever, well then you can just do this. And you get that.
That's not the.
Yeah, it is. This minus it. Right.
John, shut up. No,
Yes. Any question? I saw someone, I think.
Oh,
Yeah.
wait, isn't any integer a Trot number, a Trot constant?
Yeah, but wait, like, the point is, you want to find irrational numbers, you know, you want to
So how
find.
do you even know that Trot, that the one they kind of came up with isn't even irrational?
We don't.
So then how does he even know it's a Trot constant?
No, Trot constant just means that it's equal to its continued fraction
Yeah, but-
representation. Basically, the guy cooked up an algorithm that spits out that number. So you can calculate it up to as many decimal places as you want, and it will be the same. But he didn't prove it using theorems.
That's a bit
you know.
contrived. I think this guy.
It is a bit contrived.
He's trying too hard.
He is trying too hard. That's why he's cheating. But it is interesting, and maybe hopefully one of you in the future will be able to actually prove it instead of complaining.
That's the worst like punishment ever.
Go do a differential geometry.
Yeah.
Yes.
Can you go back to the thing where it was like the geometric mean or something?
Yeah. Yes.
Like, I don't get it. Why can't you just like plug it in and check? Like, do you not know the continued fraction representation?
Well, no, because most numbers have like non-periodic, like there's no patterns in any of your, like when I gave the Euler-Mascheroni constant when I spoke about it earlier as an example, we don't know what the pattern is.
So for most numbers, we don't actually know what the representation is.
You can calculate it, right? Using like you can cook up an algorithm that will give it to you, but it doesn't mean that you can find a pattern in there. Like to prove that there's a pattern, that's not something you can do with an algorithm, right? Like you need to sort of prove that it's periodic or
So
something.
you can't like find a formula or something like that.
No, not for most numbers. No.
Okay.
I mean, you could prove that there's no pattern, maybe, right? And then in that case, you wouldn't be able to
Yeah, I guess.
use this. Yes.
So you can like even if you don't know like the pattern or anything, you can still like plug in like some digits to just test if it's coming close to it.
Yeah, you could test, but that's not the same thing as
No,
proving.
I know, but is it looking good?
I actually don't know. I mean, the thing is, there are infinitely many numbers, right? So it depends
No.
depends on the number you test.
Drawer disagrees.
Well, actually, we don't know if you can test it out for pi, and maybe you can try to get arbitrarily close, but that's not the same thing as proving it, right?
Yeah,
so
no, I'm
maybe
just curious.
after like a billion terms, it like diverges, or like like
Yeah.
we don't actually know, right?
So basically, all the numbers we actually know if like the continued fraction figure for this doesn't work.
I guess I would say all the numbers that the continued fraction has like a formula that we can write down
Right.
doesn't work. Yeah,
Okay.
yeah, or at least up to the ones that I know of.
So
Maybe
why does it fail for E? How do we know it fails for E?
There's like a paper you can read the paper. I don't know the proof of why it fails for. Well, I guess wait, maybe we can sort of figure it out, right? Because let's believe that what was the continued fraction representation for E, right? It was like 1, 2, 1, 1, 4, 1. Is that what it was?
Yeah, 1, 6.
Is that what I said? Was it 1, 6 or 1, 8?
I think 1, 6.
Was it 1,
Yeah,
6?
6.
Yeah. Okay.
Yeah.
1, 6, 1. I guess what is the geometric mean of the first n terms? Well, I guess if you can look at the first, I don't know, if it's the first 3n, like the first multiple of 3 terms, this is just equal to like 2 times 4, right? And then it's equal to 2 times 4 times 6 times. So, actually, you know what, that would be a fun exercise. You guys can try doing that later on your own time. Yes?
Was this actually continuous constant inspired by a certain spreadsheet?
Yes, perhaps. Maybe.
What spreadsheet?
No, it's so. The funny thing is, so like at the math union, we try to plan like the dates of our events based on constants, and we had an event planned on Kinshin's constant day, which was February 6th. Did you say February 7th? I don't know.
You round up?
We round up. I mean, if there was a February 68th, we would have held it on that day. But alas. Yes. Any other questions? Yes.
Also, from most numbers we can't check by plugging in because uncomputed numbers, right?
For which number?
For uncomputed numbers, for example, we can't have those
For uncomputable numbers. I mean, yeah, I guess, yeah, you obviously.
which are also
Right. Well, I mean, who cares about uncomputable numbers anyway?
I do.
Uncomputable, right? No, I don't believe in uncomputable numbers. Yeah. Any other questions? All right, I guess we're good then. Chris, where's the pizza?
What?
Where's the pizza?
What do you mean? Puss!